paper is written by Benjamin Gregoire, Jean-Christophe Léchenet, and Enrico Tassi, and Enrico will give the talk.
Can you hear me? Does the mic work? Yep, so. Okay, hello, thanks for showing up. So the objective of this work is to make the marriage between these two software projects actually work. On the left, we have the mathematical components library, and you see the hierarchy of interfaces around which the contents of the library are organized, and on top, the interface of types that are equipped with an equality test. And on the right-hand side, you have the Jasmin language for high-speed cryptography. Its compiler is certified in COC using the mathcomp library. As you may imagine, most of the data types in the compiler are discrete, so they have an equality test. But still, you have to convince COC about that. Okay? And there are three problems in this marriage. The first one is that some data types are very large, like this one, that model the instruction set of a CPU. And COC comes with some commands here to synthesize automatically the quality test. And then there is some boilerplate to link it to the library. If we fast forward to the conclusions of the paper, well, the command we were invoking is this blue line here, which is cubic. Today we are here. The instruction set doesn't include, for example, floating points instructions. So if we add them, we are going to be here. So, well, it doesn't look good. While in this work, we managed to be down here. So we don't fear anymore the instruction set to grow. The second problem is that sometimes the tools you have are not just slow, but just don't work. Here, for example, is the data type of words, which is parameterized by the size of the words, and it is a dependent pair packaging an integer and a proof that the integer is between 0 and 2 to the power of the size. And yeah, that's a dependent type. And here, for example, is the data type of values, where you mentioned that in this case, you have a words of some size S. And the tool doesn't work. We would like it to work automatically, but also to be smart. And for example, ignore this component here, which is a proof component of a decidable property. And in COC, we know that these have a unique inhabitants, so we could just discard them when we compare words rather than compare them. And the third problem is that sometimes the tool kind of work, but force you to state your data types and everything in a weird way. For example, here the data type of instructions. If we look at the if node, there is an expression and two branches. And we would like to say that a branch, each branch is just a list of instructions paired with some info. But because of the use of containers, the tools don't quite work. So in practice, the thing is written like this. You do a mutually inductive type with a copy of the pairing constructor. Still, the induction principle generated by COC is too weak, so you do it by hand. And it is folklore how to do it, but you have to kind of inline the induction principle for lists. So you will have an hypothesis and two premises talking about nil and cons, while well, I don't find it particularly pleasing. So in the paper, I will focus on, in the talk, I will focus on the first problem. In the paper, we also address the other two. I give you quickly the idea of how to simplify things for dependent types. And if we go back at the value type, imagine when you are comparing two words in this case, you will have two sizes and two words. And you would like to reuse the code to compare words. Okay, if you synthesize it in the obvious and homogeneous way, it will end up like the first line. So the words would have the same size, and you would have trouble just calling your code. While if you systematically synthesize heterogeneous on the parameters equality test, then you can just call your code in this case, because you will have two sizes and two words of these sizes. Okay. Then in the proof, you will figure out that the sizes are the same, and you will proceed having words of the same size. But at least in writing the test, it's much easier if you are always heterogeneous. And the third thing was already addressed about generating induction principles which are strong enough to prove the soundness of the quality tests in another paper of mine. In this one, we do a better job explaining how these deep induction principles can actually be used. Sometimes you need to resort to some functoriality properties that are derived automatically, but I think in this paper we better explain how you use them. Okay? So going back to the performance problem, this is the natural code you would write for an equality test on two natural numbers. Coq gives you a nicer surface syntax, but behind the scenes, this is really the term that you would write, which is you would pattern match on the first natural number, and in each branch, you would pattern match on the second natural number. If the constructor happens to be different, like in this branch and in that branch, you would say false. If the constructor are the same, then you are in the interesting diagonal here, and you either conclude true in the first case, or you do the recursive call on the subterms, like in the last branch. And as you can see here, you're building a square, so you're not linear. And the problem shows up also in the proofs. The proofs are two directions. One is reflexivity, and here you have only one variable, so induction is sufficient to explore all possibilities. But when you prove the other direction, that if your test returns true, then your natural numbers are actually equal, you need to expect both. So one time by the induction hypothesis, and the other one with an explicit reasoning by cases in both branches. And if we look at the branches that correspond to the false branches of the code up there, they are both absurd, but they are different. You cannot share them. Here we are comparing 0 with the successor of Q that comes from the second guy, while here we are comparing the successor of P with 0, very similar, but different. P comes from the first guy this time. So it's very hard to compress this proof more than that. And again, it is quadratic. And one way to see the problem is that we are using our beloved pattern matching construct to do two things at the same time, both comparing the names of the constructors and accessing the fields of each constructor. So the core idea is quite simple, is to split the two steps, give a first-class representation to constructor names. For example, if we are building the quality test for a type A, we need a tag function to give us like a positive number corresponding to the name of the constructor. Then we need a way to type the fields and to access the fields of each constructor. And finally, a way to compare the fields. And then this is the core procedure of the quality test. We start by computing the tags of the two terms. Then we compare them. If the tags are different, we say false. Okay, we are outside the diagonal, and we have only one branch with false, not many as before. If they happen to be the same, we extract the fields, and we compare them. Then, well, these fields have this type, T1, and these have the type with T2. They are different, but we just discovered that they are equal, so you need a little cast to convince the Coq tag checker that this is actually fine. But other than that, it works. So let's apply the idea to the natural numbers again. We need to associate a tag name to each constructor, 1 and 2, for example. Then the types of the fields. 0 has no arguments, so we say unit. You could put anything here. And while the successor has one subterm of type nat, then we have to inhabit the type up there. So 0, we put the inhabitant of unit, T, and here we put the subterm P. And then we need a way to compare the fields. We abstract it over the recursive call. And then we look at the tag number. In the first case, these are two inhabitants of unit, so we just say true. If there are two natural numbers, well, we do the recursive call, otherwise we say false. And remark that here we have as many branches as the number of constructors, here as the number of tags, which is the same, the number of constructors, the number of tags. So the code we synthesize is linear in the number of constructors. Okay? And then you implement your procedure, you benchmark, and you're still quadratic. So something goes wrong. But what goes wrong is very specific to Coq, so you're warned. The first problem has nothing to do with performance itself. It's just that the termination checker of Coq is too simplistic to understand that our code works. And in particular, you need to destructure the first term by hand. In a way, you are inlining the computation of the tag and the computation of the fields for the first guy you are comparing. So here we are passing to our common code the tag name and the fields, okay? And then you pass the second argument. If you write it like that and it is still linear in the number of constructors, well, the termination checker is happy, okay? The second problem, we need a data type a bit more complex than the natural numbers. We need more subterms. Here, a simple tree with a number and two subtrees. And we may think that the best way to represent the fields of node would be a triple, using really what you would write in the concrete syntax of Coq with an open parenthesis and commas. So this is the nested pair of a nut, a tree, and another tree. But unfortunately, because of implicit arguments, when you package these three things here, the number and the left and right subtrees, inside the triple, you have, even if you don't see them when you print the term or when you write it down to play, you are actually making a lot of copies of the types of these subterms. And if you look up here, you have 1 copy of nut and 2 copies of tree. And here you have 1 and 2 copies of nut and 1, 2, 3 copies of tree. So something is going wrong anyway. Well, given that we are metaprogramming the system, we can synthesize stuff as we please. So we synthesize for each constructor a monomorphic version of the tuple that can carry its arguments. And, well, we have a box for each field, for each kind of fields. And now, if we want to build the triple of the fields, it becomes trivial. Okay? It would be extremely ugly to do it by hand, but we are doing it behind the scenes. So there's no problem with that. A very similar problem arises when you are doing the proof. For example, one step in the proof is that you know that your code that is comparing the numbers and then doing the recursive calls over the subtrees returns true, and you have to prove that actually the two nodes are the same. The usual way to split this hypothesis, this conjunction in the hypothesis, is to use a lemma that splits that works on two conjuncts. Okay. But every time you use this lemma, you make a copy of the conjuncts and a copy of the goal. So imagine that it is left associative. The first time, little a would take this. The second time, it would take that. So you are duplicating stuff anyway. Okay? It's very easy in Coq to write the type of an n-ary lemma that split an n-ary conjunction. Sorry, it will take the list of conjuncts. Okay, this is a little program that generates the type of the iterated conjunction, and this is the type of all the conjuncts imply P. Okay, so you make one copy of the goal, one copy of the conjuncts, and you are done. You are linear again. A very similar problem arises when you are doing the rewriting steps. So once you have split the conjuncts by induction hypothesis or by the soundness of, for example, the comparison of natural numbers, you obtain equations and you have to replace there. And if you use the standard principle to substitute in Coq, it would substitute one equation at a time, and you pay the price of copying the goal, okay, binding the subterms you want to replace. Okay, so if you want to apply 3 equations, you need to make 3 copies of the goal: one to replace this guy, one to replace that guy, one to replace that guy. Again, it's easy in Coq to write an n-ary rewriting rule, which takes the type of the 3 guys you want to replace, and now you make one copy of the goal binding the 3 guys you want to replace, and here we pass one copy of all the terms. So again, you are linear in the number of the constructor and in the number of the fields in this particular case. Oof. So in the end, you are happy, you do the benchmarks. This one has many constructors with no fields, okay? And while this one is an inductive type with just one constructor with many fields, okay? And in both cases, our code is around linearish, okay? And while the others should be, I think, if you do the naive thing, it should be quadratic, like this one. Sometimes they are more than quadratic, I believe, for engineering problems. I mean, if you dig deep and you solve stupid issues, they should be quadratic, in my opinion. And there are even some tools like deriving, this one, which in my opinion should be linear as well, but for implementation problems it is not, as we benchmark. And a few words on the implementation. We wrote the code in CoqLP. It's quite compact. It's about 800 lines for the synthesis of the quality tests, and about the same for the generation of the induction principles, which are strong enough to deal with containers. And these are examples of data types we are able to handle. What we don't handle are mutual inductive types, because CoqLP doesn't have yet support for them. And we also don't support indexed data type like vectors. So before the word data type had a parameter which was a value, but is not an index data type for Coq. It's not that. It varies like in a vector. And so to conclude, our tool is full automatic, in this case to large inductives, but also, even if I didn't really talk about it in the talk, it supports subtype, I would say sigma types with decidable properties in it, and the containers. It's integrated with a recent release of CoQLP, so it's easy to try it out. The documentation is not super, but well, there is some. And the next steps, I think, turning our code synthesis into generating an order relation is rather easy. I really don't know about the proofs part. And another thing we may look at is that there are other parts of the system which suffer from performance problems that stem from the very same quadratic behavior, which are the discriminate and inversion tactics. So maybe we will see if we can apply the same trick to them. And that's all I wanted to say. Thanks for listening.
Thanks for the nice presentation, Enrico, and I see we have
Hi. Yeah, this is all awesome as usual. So I'm just curious kind of what the plan is for, like, what are the barriers for getting kind of Coq LP into the Coq release itself, so that it's just kind of part of the system? Because I feel like a lot of these utilities seem as like kind of core to proof development as like inferring just a plain old induction principle to begin with. So I'd love it there.
So, okay, I have two little answers. One, CoQLP is part of the Coq platform. So if you install the platform, you get CoQLP. I think, I hope one day I will put it in Coq proper. Today, it lacks two things that I think should be ironed out before doing that. One is mutual inductive, as I mentioned, even if, I mean, it depends what you do, but in some areas you really need mutual inductives. And the other is universe polymorphism, which is kind of supported in CoQLP, but I'm not happy at all about how it is done. Once these two things are in a better shape, I will push it inside. I hope it's not too bad.
Thanks for the talk, and that looks super impressive. But it seems like you needed to spend quite a bit of time to get actually to this linear time. I was wondering if like Coq had proper support for sharing common subterms, how much of that work would have been necessary? Or
so I briefly mentioned in one slide here. So, for example, you could share these two branches, okay? And actually, Benjamin Gregoire is another author of the paper, had a patch for Coq with a compact representation of the pattern matching. Okay. So the quality test can be represented in Coq in a smaller, in linear space, but the proof is going to be still quadratic. As I was mentioning, the two absorb branches are different in the binders. It's not just if you look at the two false branches, they actually ignore the argument of the successor in the first one, and the second one is the zero. So the two pieces of code can easily be shared, but here in the proof is really not the case. So
yeah, okay. But like
there is a note by Benjamin in the paper about the fact that we couldn't apply his idea here.
Okay, for the later parts where you showed like with the Boolean and so on?
For implicit arguments?
For the implicit arguments, yeah.
So for the Boolean conjunction, I would say if we had proper sharing, yes, I think it would stay linear. We wouldn't need to do the trickery. For the rewriting, I think it would still be a problem. Where is it? Because here again, the left-hand side can still be shared, okay, but the right-hand side is different trees. because you have to bind the pieces. So I'm not so sure you could compact it completely.
Okay, thanks.
Do we have more questions? Okay, it doesn't seem to be the case. Then let's thank Enrico